Hi, I'm Hüseyin Ömer Demirci. My school ID is 2022-40-12-13. Today I'm going to tell you about my term project. In our term project, we will do an optical current sensor, which will use a photodiode, in our case a red LED, as a light sensor. And then we will read the current through a transimpedance amplifier because the current will be very small, like in nanoamps, picoamps region. We will do that in part 1 by measuring an output voltage and dividing it to our feedback resistor, and in part 2 by measuring an output voltage and using dV over dt on our oscilloscope and multiplying it with a capacitor. Let's get to the part 1. In part 1, this is our circuit's configuration. We will measure the current through the feedback resistor. Our LED is connected to the feedback path, and the output we will measure the voltage of. And we will do that on 3 conditions: one on ambient lighting, one on flashlight, and one on complete darkness. Let's get to the measurements.
1.
First, we will measure on the ambient lighting. Let's get to the measurements. One and in the output terminal, one and on the ground. Let me just not make shadows here. And we read about 1.4 millivolts. Now we will measure it using a flashlight on our phones to see if it increases or not. Let's get the flashlight. As you can see, it increases to around 400 millivolts even.
1.
Now we will measure it under the darkness. Sorry for the setup, it's kind of bulky. We are reading around -3 millivolts, which I will explain in the next part of the video. We know that our op-amp has an input offset voltage. We need to measure it. To measure it more precisely, we can construct a inverting amplifier which has gain 1000, as you can see, from 10 resistor and 10K resistor. By using that, we can see that whatever value we read here will be our offset voltage times gain. Now let's do the measurement for our bias voltage. As you can see, we are reading about -3 volts. As I said before, our gain is -100 volts, and we read -3 volts for our output terminal. That means we have an offset of -3 millivolts. So when we put anything to our inverting terminal of our op-amp, the value we read will be 3 millivolts lower than the actual value. As you can see, on our ambient lighting conditions, we read 1.4 millivolts on our output terminal. Without normalization for the offset voltage, that gives us 1.4 times 10 to the -3 over 10 to the 7, which is equal to 1.4 times 10 to the -10, which is approximately 140 picoamps. Now let's try and normalize it with our offset voltage. As I said before, our offset voltage is -3 millivolts. That means our actual value with normalization with respect to the offset voltage is 4.4 millivolts. Which means we have 440 picoamps on ambient conditions. See, when our flashlight was open, we read 401 millivolts from our multimeter. Knowing that it went through a 10 megohm resistor as before, we have 40.1 nanoamps without normalization for the offset voltage, and when we normalize it with the offset voltage by adding 3 to that, which means 404 millivolts, that goes to 40.4 nanoamps, which, as you can see, makes very little difference when the flashlight is on. As you can see, we are reading -2.9 millivolts for the dark conditions. So let's divide it by our feedback resistance. And to the -10, which goes to around -290 picoamps. You can be asking why is it minus? Because we haven't normalized it with respect to the offset voltage yet. So let's just normalize it. Plus 3 millivolts, which is equal to 0.1 millivolts. So let's now divide it by our resistance. 0.1 times 10 to the minus 10 amps, which is equal to 10 picoamps as the dark current, which is more or less in the expected region.
1.
On part 2 of our experiment, we are going to measure the voltage on our feedback loop capacitor and take the derivative of it and then multiply it by our capacitor to find the loop that's going through the feedback. That means that's being supplied by our LED. The connections are as shown here. We have a short circuit here to ensure that our capacitor is empty at the start, and then we are going to use some oscilloscope settings that I'm going to show you in a bit, and then remove the short circuit and see how the voltage on the capacitor changes. Let's get to it. On the part 1 of the experiment, we are going to measure the current that's being produced by the ambient lighting. Our setup is as we described. Our volt per division is at 10 volt, and we limited our bandwidth to 20 hertz to get rid of the 20 megahertz to get rid of the noise. Our time per division is at 1 second. Our trigger is at 1.2 volts, which is all amplified by times 10 because we have times 10 probing on our oscilloscope. I already did the settings, so let's just press the single sec to get it ready for the measurements. As you can see, it has turned ready here. So now let's get rid of the short circuit. And let's see the waveform. As you can see, we have a positive slope. Now for part 2 of the circuit, we are going to measure it under the flashlight of the phone. Our settings are as follows. We have 10 volts bandwidth limited voltage division and 250 milliseconds this time because the slope will be a bit steeper, and to be able to observe better, I just lessened our time division, and 1.2 volts is the trigger, which corresponds to 120 millivolts again. So let's just press the single sec. It's ready. Now let's short circuit it. As you can see, the slope is still very steep, so maybe let's just mess with the time per division a bit more. Up. And the slope is here, as you can see. On the next part, we will need to measure the current when the LED is covered. For that, I brought the bypass capacitors closer to the op-amp pins and got the node from here to the closer to op-amp to get rid of the noise as much as possible. So let's now do the calculation. As you can see, we have covered our LED. Let's get through the oscilloscope settings once more. We have 1 volt per division here with bandwidth limited. To see the slope better, we have now 2.5 seconds instead of regular 1 or 0.5 because the slope will be a lot less steep. So to be able to see that, we need a better time reading, and our trigger is again around 1.2 volt, which corresponds to 120 millivolts. So let's press the single sec. Wait for it to get ready. It's gonna take a bit of a time because the capacitor charges very slowly with that current, and the waveform will take a time to generate. So let's now get rid of the short circuits. Let's wait for our waveform to generate. As you can see, we have our slope here. Now let me show you the setup I used to find the bias current. To be fair, the bias current will be similar to the current that we found when we covered the LED, but to be precise, let's still measure it without the LED. As you can see, I've opened where the LED is, got the bypass capacitors closer to the op-amp pins, shorted my capacitor. So let's get to the measurement. Here's our measurement setup. Our settings are pretty similar. It's 1 volts per division, bandwidth limited, 2.5 seconds per division, and 1.2 volts on trigger, which corresponds to 120 millivolts again. So let me just press the single sec button. Let's wait for it to get ready. Now it's ready, so let's get rid of the short circuit. Wait for it to trigger and give us the waveform. It's again gonna take a while because the capacitor is charging up very slowly because the current that's going through it is very small. Now it's triggered. Let's wait until we get the waveform. And here is the waveform. As you can see, it has a positive slope with a lot of noise on it. Start by calculating our offset current for the integrator circuit to be able to normalize our other current calculations afterwards. As you can see, we reached to around 1.4 volt in 5 full divisions of 2.5 seconds, which corresponds to 12.5 seconds. When we divide those two, we get 0.112 volts per second, and our capacitance is 10 to the minus 9, and we can multiply it by 0.112 volts per second, which gives us our current, which is 0.112 nanoamps, which is 11.2 picoamps. That 11.2 picoamps is our offset input current. So now we can get to the measurement calculation of our dark current. When we cover the LED with a dark cloud, we get 0.14 volts over 9 seconds on our voltage. As you can see here, 1.4 volts, 9 seconds. But the probing is times 10, so 0.14 volt over 9 seconds, which gives us 0.15 volts per second. And our current is then given by 10 to the minus 9 times 0.15, which is equal to 15 picoamps without normalization of the offset current. But we know that our offset current is 11.2 picoamps. Therefore, our actual current is 15 minus 11.2, which is equal to 3.8 picoamps, which is more or less zero given that the LED is covered by a dark cloud. So the photocurrent will be more or less zero. Now let's do the calculation for the ambient light. As you can see, or maybe you can't, I'm not really sure about resolution, 2, 4, 6 volts, 1.2 seconds. But the probing is at times 10, therefore 0.6 volts over 1.2 seconds, which gives us 0.5 volts per second. Our current is then given by capacitance times 0.5, which is equal to 0.5 nanoamps. But recall that this current is not normalized, which means to normalize it, we need to subtract 11.2 picoamps from it, which gives us 488.8 picoamps, which is 0.49 even nanoamps under the ambient lighting condition, which is very close to our transimpedance amplifier measurements. Now let us compute the current for the flashlight condition. As you can see, we reach to 20 volts in 1.2 divisions of 25 milliseconds, which corresponds to 20 volts over 30 milliseconds. But our probing is again on times 10, therefore 2 volts over 30 milliseconds, which gives us 66.67 volts per second. To find the current, again, we multiply that value by our capacitance, which gives us 66.67 nanoamps. And we can normalize that value, but it's like around 66k picoamps, and just, subtracting 11 picoamps from it does nothing. Therefore, we can just say the actual current is around 66.67 nanoamps, which is a bit higher than our transimpedance measurement. And with those measurements completed, it brings us to the end of our experiment. So let's talk a bit about our conclusions and what we found. So the conclusion the measurements were pretty much as expected. When the light that's been on the LED increased, the current that has came from the LED also increased. There were some difficulties, obviously, which was due to the noise of the environment mainly, and some measurements that are like I left my multimeter on millivolt AC instead of millivolt DC for the first part of the experiment and needed to redo all the video. And the noise I couldn't really get rid of, as you can see on the oscilloscope measurements for dark LED and no LED, but I think it doesn't get much better than that. And to go over our measurements once more and compare them with each other, on the transimpedance amplifier and on the integrator, we had the offsets in expected ranges. Actually, on the offset current of the integrator was a bit lower than the expected 30 picoamps, but I'm guessing that's due to noise and my measurement errors. That doesn't matter that much. And as you can see, on the dark condition, we read 10 picoamps and 3.8 picoamps. Here, integrator should be a bit more reliable due to it not being bounded by the precision of the multimeter. On the ambient light, we actually read very similar values, which means our measurements were consistent and our measurement methods were correct on both parts. And on the light part, we can see a difference of around 26 nanoamps, which seems like a lot, but actually it can just be due to us holding the flashlight a bit closer or a bit further away from the LED, I think. Thanks for listening to me.